Good evening. On behalf of Engineers Australia, I'm delighted to welcome you all to our Infrastructure Thought Leaders series on Double Wall, the Precast Evolution. Firstly, in keeping with our tradition, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders past, present and emerging. Our speakers this evening will discuss the evolution of double-wall precast building systems. Widely used in commercial construction throughout Europe, thanks to its many benefits in engineering, design and construction, double wall is a permanent formwork precast building system, which enables the creation of monolithic structures. With the building boom continuing to grow, this innovative solution enables better engineering design, increases efficiency on site, and reduces construction challenges. Our speakers will reference local and global case studies to discuss the evolution and innovation behind double wall and how, as a permanent formwork system, it enables quality, efficiency and flexibility to projects. They will discuss the advantages in the installation and the benefits of a shorter superstructure construction time. Before we get started, I'd like to acknowledge that tonight's seminar is being hosted with our industry partner, Austral Precast. Austral Precast is a leading provider of high-quality, customisable precast concrete product solutions, operating from plants located across Australia using state-of-the-art technology, production techniques and systems. Austral Precast produces a diversified range of products and precast solutions. Austral Precast services a range of markets, including multi-residential, commercial, industrial, community and civil sectors. I'd now like to welcome our first speaker, Matthew Murray. Matthew is the Engineering and Estimating Manager at Austral Precast and one of Australia's leading experts on double wall. Having worked with countless clients on various projects that range from tunnels, including the M5 project in Sydney, and high-rise buildings, Matthew developed an intimate understanding of the double wall product and how it can be used to improve engineering design and construction timelines. Please join me in welcoming Matthew Murray.
Thank you, Amanda. Hi, everybody. Thanks for attending tonight this event for Engineers Australia for Precast Evolution with Double Wall. I'm Matthew Murray, the Engineering and Estimating Manager from Austral Precast, and I'm very glad to talk to you about double wall tonight and the benefits it can bring to the construction process in Australia. So just a little bit of background. Austral Precast is a subsidiary of the Brickworks Building Products Group, which is an ASX 200 company, which has many brands you might be familiar with, such as Austral Bricks, Austral Masonry, Bristile Roofing, and we have many plants both in Australia and New Zealand, and now also with manufacturing operations of bricks in the United States as well. So we've now graduated to being a truly multinational company. Here's just a little snippet of double wall.
Build with confidence with Austral Precast Double Wall, a permanent formwork system that brings quality, efficiency and flexibility to any construction project. Double wall uniquely combines the advantages of precast construction together with the engineering benefits of in situ construction. Fast and economical site processes, yet with flexibility for individual planning and architectural objectives. Double wall is the perfect solution for today's construction needs. Austral Precast Double Wall consists of a pair of precast reinforced concrete shells forming a cavity and connected by a lattice girder fabricated from reinforcement bar. Double wall is finished with joints and corners that minimize the need for on-site caulking, welding and formwork. Provisions for formwork with doorways and windows, electrical, cable, air conditioning and plumbing conduits are fully customizable. And overall wall thickness can vary between 180mm to 400mm, depending on each project's individual structure and applied load requirements. On-site, double wall's hollow wall design structure allows for easier installation due to reduced weight crane loads. When cavities are filled with premixed concrete, double wall forms a strong and solid concrete structure. And unlike other permanent formwork systems, double wall has the added advantage of being installed with reinforcing for structural loads already incorporated into the product, eliminating 90% of the on-site steel fixing ordinarily required on-site. The results are ready-to-paint perfect facades where smooth surfaces are achieved on both inner and outer walls. Austral Precast Double Wall is your ideal solution for stairs, lift shafts and basement walls, facades, cladding and retaining walls, functional partitions, noise, fire and sound barriers. And with the advantages of watertight construction and excellent thermal performance, build with confidence with Austral Precast Double Wall, the smart and efficient permanent formwork system.
Double wall is a permanent formwork system with all the quality and efficiency advantages of precast manufacture, together with the engineering benefits of in-situ construction. So what is the major difference between double wall and a traditional in-situ structure? On the left-hand side here, we can see both plan and section views of a typical concrete wall with each face reinforcement shown in red and the starter bars in the slab in the darker colour. On the right-hand side, we have a double wall. The major difference here is that you can see that the double wall has the panel system, which means that there is discontinuity at the joint, and that continuity of reinforcement is made by lapping steel at the joint in the core. So here you can see the red bars represent the each face reinforcement in each precast shell, with each precast shell being connected by the lattice girder shown in green. The only difference structurally from a double wall to an in-situ wall is that the starter bars and the joint reinforcement have to be in the core of the panel in order to get continuity of the connections. So for instance, here on the left-hand side here, we can see the starter bars with essentially the same separation as the vertical bars, but in the double wall, will be a slight reduction in the spacing of the bars due to the bars having to be in the cavity. So double wall is a structural wall. The main thing for double wall is that the shell thickness is critical to the overall structure and the temporary works of the product. So shell thicknesses can be made from 55 to 70 mils, with 70 mils being the standard size of our formwork in our factory. The core of double wall requires a minimum thickness of 70 mil, and this is so that we can get the starter bars and any joint reinforcement into that core prior to concreting on site. The site concrete typically is a minimum of 40 MPa with 10 mil ag and 180 mil slump, and the reason for that is using the 10 mil ag and the higher slump is so that we can make the concrete pumpable and to get adequate core filling in the core. All the reinforcement that you would have in the in-situ wall is included in the precast shells of the double wall. The lattice girders that you can see here connect the two shells together, and they serve two functions. The first function is to connect the two shells together in the temporary state. So the embedment of the vertical bars of the lattice girder requires at least a minimum of 15 millimeters to connect the two shells together. But then the second function as well is to make the wall act as a composite structure. The reinforcement that crosses the interface from the lattice girder contributes significantly to this. All the inserts or casting items are included in the double wall. So for instance, here we can see lifting hooks that have been highlighted in blue for lifting on site, which are cast into the wall and do not require any extra treatment after the panel has been core filled, as they remain within the cavity. The typical thicknesses of double wall range from 170 through to 400 millimeters, but the shell thickness for the double wall remains the same irrespective of the size. So for instance, a 250 mil double wall with 70 mil shells would weigh the exact same weight as a 400 mil double wall with 70 mil shells. The advantage of this is that the crane size is not limited by the overall thickness of the wall on site, but only by the shell thickness, which is a big advantage over traditional precast construction. Austral Precast has a maximum pallet casting size of 3.5 meters by 13.2 meters for a standard double wall, with masses ranging from 265 kilograms per square meter of panel up to 375 kilograms per square meter, largely dependent upon the thickness of the shell, going from 55 to 70 millimeters. So how do we actually manufacture double wall? The manufacturing is predominantly done in 2 stages of each concrete shell with a flipping component in between. So on day 1, we make the first shell of the double wall, which has all the concrete and reinforcement and girders in the first shell. That is then cured overnight to reach a minimum of 20 MPa strength. Once that has reached 20 MPa strength, that first shell is taken out of the curing chamber, put onto our pallet flipping mechanism, inverted 180 degrees. Then the second shell is poured with the reinforcement in the second shell before the 2 shells are joined together. So here's an example of how we actually do this in the factory. So what we're looking at here is an example of 2 panels that are cast on the pallet that were made in the factory yesterday. So this panel here contains the precast shells of 70 mm thick with the lattice girders that you can see running up and down the page. And for this particular product, we have some U-bar connections at the sides of the panel. The clamping that you can see on the pallet is in red and yellow and blue there are essentially steel bars that clamp the pallet to the table, and that is achieved through a hydraulic which cantilevers off the long yellow bars there we can see of the pallet flipping mechanism. So once that is ready to flip, the pallet is then raised above the station. The subsequent shell 2 is then poured, and that we can see here. So here we can see a 70 mm thick section that has all the concrete and reinforcement in shell 2 ready to go. And then we flip this into the next pallet. So here we can see the flipping motion. This is a time lapse, it's slightly faster, but essentially what we are doing here is clamping the table above, inverting it 180 degrees, and then lowering it into the next pallet. Now, there's a couple of key little things here. If we could pause the video. Here we can see there's some tapered pins on the pallet. So that's really critical in aligning the 2 pallets together that we can see here on the left-hand side. So here we can see the tapered pins on the left-hand side here. So essentially that does 2 operations. That separates the 2 pallets from one another and stops the pallet from crushing the panel below, and also centers that pallet to the pallet below. The panels themselves have some spaces in them, to help separate the 2 shells apart and to control the thickness. So once the pallet has been flipped, the pallet above is removed and the double wall is then put into the chamber, ready for its final curing stage before going to site. So here we can see some of these panels that have been made in the factory. So typical construction manufacture methods has the double wall being made in the factory, lifted off the table using an overhead crane, and then put into storage in our factory. Once the site is ready for construction, the panels are delivered to site on A-frame and stood and propped as you would with traditional precast using temporary bracing. For construction on site, there's a couple of key processes. Firstly, the starter bar setout must be installed by the contractor prior to the delivery of the panels, as the starter bar in the base of the panel completes the connection of the vertical reinforcement from the slab to the panel. And Austral Precast provides a starter bar layout in DWG format for surveyors and site installers, so that the layout can be done in accordance with the drawings. Once the panel has been lifted, the panel is placed over the starter bars in the correct location and propped using temporary bracing, as you can see on the right-hand side. At this point in time, the joint reinforcement is placed inside the core of the cavity. So in this case here, you can see the gentleman on the boom has a mesh that has been made off our mesh machine and being placed into the cavity. The subsequent panels are then placed, and the next day the panels are then ready for core filling. So when it comes to core filling, we use typically a 10 mil ag, 180 or 200 mil slump concrete, and this can be done by either boom pump, kibble, or other methods. And the advantage of double wall is that you can also install the concrete on site either before or after your slab has been erected. So you can pour double wall from the deck of your slab, or you can pour the double wall prior to the slab being installed, and any ends of panel can be any pour breaks can be set out with a construction mesh being put into the core of the panel, so that in case the complete wall is not finished, you can actually have different stages of construction. So when it comes to the design of double wall, Austral Precast has a technical manual available online that is in line with the current Australian standard regulations. So AS 3600 2018, concrete structures. So we have details available for compliance with all the new detailing design under section 14 of AS 3600, including provisions for boundary elements. Also, the design is done in accordance with AS 3610 for formwork. So that is largely the sizing and overall shape of the concrete walls, and the finish, which for double wall is a class 2 steel bed table face finish on each side, and then for AS 3850 for the temporary erection of double wall. Where there is no current Australian standards available, we go to the European regulations for double wall, and this is in regards to the tolerances of the panels themselves. So that's largely has to do with the embedment of the girders, the pouring rates that can be achieved, the lifting specification. So the double wall lifters that we are utilizing a 3 times factor of safety as per the European regulation, which has been in use for over 20 years, and also the principle of any calculation. Specific details are also available for, as I said before, for boundary elements and also for joint details. So as part of our technical manual, we also have the standard sizings available. So the key with double wall is the internal cover from the inside of the longitudinal bars of the girders and the core. It's the most critical part for the temporary state. So typically we need this C-min value that you can see here on the picture on the left to be at least a minimum of 15 millimeters, and the size of the girder and the overall thickness of the panel will be dictated by not by the overall size of the wall that's required, the cover, and typically the horizontal bars, as the girders sit on the horizontal bars of the panel. Sorry. We also have load capacity tables available based upon the minimum reinforcement requirements and the different thickness of walls. So a key component for double wall is where there are no regulations available, we have gone to the European regulations, specifically the French regulation, which has been around for many years. So overseas, double wall is currently manufacturing in excess of 6 million square meters alone in France, and they have been doing so since with double wall beginning there in 1991. And today it is the predominant precast manufacturer. So one of the key sections of their code that we can see here is what to do for the compressive section calculation with double wall. So traditional precast in Australia uses solid wall precast with a mortar bed. On the left-hand side here, we can see a double wall with no mortar bed and only using a 10 mil spacer. When the concrete is core filled into the panel, if we have a space of less than 1.5 times the diameter of the aggregate size, then the concrete will not be able to fill that gap. So here, if we had a 10 mil aggregate for our first picture on the left, and only a 10 mil space at the base of our panel, the compressive section that we can only use reliably as far as an engineering calculation would go would be the core of the panel. So if this was, say, a 250 mil panel with 70 mil shells, that would only be 110 mil thick, which may or may not work for the structure. In the event that the space under the panel cannot be achieved, but we still want to have the full compressive strength of the panel, we can use mortar on the joint as per the middle drawing here. So in that case, if the joint was less than 1.5 times diameter, a mortar bed could be applied either pre or post pouring of the panel in order to provide the full compressive section of the wall. Our preferred option at Austral Precast is to reduce the use of grout, not only due to the cost on site, but also due to the inherent nature of relying on employees on site, workers on site to make sure this is correct. And I think in light of recent engineering faults that have happened in Australia, this is our preferred option. So for that, we will typically use a nominal 30mm spacer at the base of the panel, and this will allow the concrete to get underneath the panel. So the picture on the right-hand side here that you can see shows the two spacers in black. There will be a pair of spacers 600mm in from either end of the panel. So they might only be, say, 100mm in length each, and then the concrete of the core fill will then be underneath the remaining section of the panel. So essentially, this gives us full continuity of concrete between the double wall and the panel, which is our preferred option and is a far more robust method of construction on site. Another section where we use the European regulation is within regards to the joint shear capacity. So the joint shear capacity is dictated by how we do the connection in the core. So in our two images here, we have two cases. The first has just 2 bars of reinforcement inside the core itself, and so for that section, the shear capacity is purely dictated by this section of the core. So similarly to our compressive strength section, if there's nothing joining the two, it is the section of the core that is taking all the capacity in shear, and the lapping is only occurring from bar to bar that we can see this. So we get so you can get a full lap from the bar in blue to the bars in orange that are in the core. On the right-hand side here, we have what we call our stitch connection, which essentially uses a U-bar cast into the panel on the right with the hairpin on the left. And what we are doing here essentially is providing a full tension lap for the hairpin on the left-hand side, which enables us to be able to have a full tension lap and go past the girder. So the panel on the left is installed first, the hairpins are installed, then the panel on the right before this hairpin is pulled across and a vertical bar dropped to tight in place. And the difference with this is that we can get the full tension lap and have the connection with the U-bar to actually increase the capacity of the joint, because there is a contribution at the joint level from the U-bar crossing the interface from the precast to the core concrete, as well as the fact that we are having essentially a cogged lapping at that connection. When it comes to the coefficient of friction and cohesion to use, there's 2 numbers which are the same as what we would use under AS 3600. So typically a C of 0.2 and mu of 0.6 for most cases, and under seismic conditions, the coefficient of cohesion C should be reduced to 0.1. Pouring rates. With every site, every contractor wants to fill the panels as fast as possible. And the major thing that dictates this is the capacity of the girders to withstand the hydrostatic pressure of the concrete on site. So here we have the situation where we can see the girder spacing ranging from a minimum of 300mm up to 600mm. So 300mm is the minimum spacing that we do for the girders for double as per the European regulations, and a maximum spacing of 600mm. So when the shear capacity of the panel is not limited by the girder spacing, the next factor would then be the concreting of the core. So for instance, here we can see if we have girder spacing of a 400mm section, we can core fill the double walls reliably at close to 1.4, 1.5 meters per hour. The main thing for this is that the girders require a minimum of 15 millimeters of cover, and we can increase these rates slightly if the cover is increased, but that will all come down to the size of the panel. From our perspective, it's more reliable just to rely purely on the minimum of 15 and the spacing, which is easier for design and construction, and also making sure that the concreter and the contractor on site are aware of the variation caused by temperature on the hydrostatic nature of concrete. So essentially, the colder the concrete is, the higher the pressure that it will provide, as it will stay hydrostatic for longer compared to when it's above 15 degrees Celsius. So here we can see some different connections for double wall. So these are purely hinged connections, which relies only on essentially the each face reinforcement in the core, which is our most simple connection and for many applications is applicable. If we want to have a more robust connection due to the structural requirements of the wall, say for instance a core wall or a retaining wall, then we can go to a fixed connection. So what we do with the fixed connection is we provide a U-bar that is cast into the panel and then a stirrup that is placed on site to essentially tie the two shells together. This section requires the one edge of the shell to be shorter than the other to expose the U-bar, which leaves an opening on site for placement of the stirrup, which is then completed with formwork on site. For a retaining wall or a water retaining structure, we can also have a protruding U-bar at the base of panel, whereby the slab is poured in conjunction with the first section of the base of the wall, and this helps with the continuity of the concrete and for a more durable construction when it comes to waterproofing for water retaining structures. Joint treatment. So double wall can be treated typically the same as you would traditional precast. So above ground, we will be using a backing rod for the panel joint to stop any slurry coming out of the panel during core filling, and that can then be completed either before or after core filling. A caulking can be applied to that for a traditional precast finish. On the left-hand side here, we have an example where we have a wall that is in contact with the ground, for instance, a basement wall. In this case, we'll use a bituminous impregnated foam cord that is stuck to the first panel before the second panel is placed. So the main advantage of doing it this way, the bituminous foam cord has a better sealing for any contaminants or water coming into the joint, and it's more durable. And from a construction perspective, this allows us to actually not require access behind the wall during construction. So we land the first panel, apply the bituminous impregnated foam cord to the joint, which is essentially sticks onto the edge of the panel, and then install the subsequent panel. So here are some projects that we've done with double wall in Australia. So Austral Precast's first job was for Wynyard Walk Station in Sydney, and these were some large 400mm thick walls with heavy reinforcement up against a boundary wall. By all means, this was a very good project and the first one for getting off the ground at Austral. In the last 2 years now, we have completed another 22 projects since launching double wall to the market in a more structured approach and with more intent on the design and specification. And so here we can see one of our first data centers we did with double wall for AW Edwards for the Equinix SY5 data center in Mascot in Sydney. For this project, we used double wall both for the retaining tank walls. So that's the picture on the left-hand side. These walls are actually the water retaining tank for the cooling liquid for the data center. But we also use the double wall for the shear walls internally in the building. So every shear wall that connected to a large precast column was double wall with a wet joint to connect the two together, which completely eliminated the use of any cast-in plates on site and any hot works for the double wall and column interfaces. Another successful project here recently is the Green Slopes Private Hospital that was completed in 2020 for John Holland in conjunction with Bly Tanner. So here we can see double height spin-up panels for a very large lift core and stair core for Green Slopes Private Hospital. So one of the main things here is the cores are much larger than a typical lift and stair core, and as a result, with the casting sizes that we were able to do double height, which is 3 meters in height for the 2 floors, and also 3.5 meter wide panels, which suited the size and shaping of the core. So the big advantage here is with double wall, there's no casting plates and there's no starter bar grout tubes compared to traditional precast. So when it comes to installing these panels, we provided John Holland with a starter bar layout to ensure that all these starter bars were correct. And once that was confirmed on site, which the guys from John Holland did a very good job of, the panels were installed typically in 10 to 15 minutes per panel. If you compare this with traditional precast, where we might have, say, a dozen starter bars that might be N28s, N32s, 1.5 meter length protruding into the panel, it was a much more easier construction process, and the overall result was very good for John Holland. So here's some of the specific details that we used for the hospital. So essentially here we have the starter bars with the 30mm packer for the bottom of panel connection. On the right hand side here, we have near the door opening, we would have a cage in one panel and a U-bar in the adjacent panel, whereby a hairpin was inserted into the panel on the left hand side before being pulled over on site and the vertical bars placed. On the right hand side here, we can see the connection for using stirrups with 2 U-bars to complete the fixed connection. So one of the advantages of double wall is that we utilized a modular formwork system. We came up with a modular formwork system for manufacturing and installation of the panels. So here, for those openings of the connections we saw prior, we have the formwork shown here in green with a bracing plate shown in red. So essentially the panels come with ferrules installed in the panel. The contractor can then place a piece of formwork which is the same size for each level, and just put a plate that we provided over the formwork section and then bolt it up. So this significantly reduced the formwork on site, helps reduce the stripping and construction time, and results in a very good structure for the builder, and also an inspection point from the engineer's perspective. Some other jobs we've had underway recently are the WestConnex M4, M5 link tunnels for the WestConnex project for the project team there. And here we were working with engineers from Jacobs, and essentially we had approximately 2,000 square meters of double wall. What you can see here is that we actually have what we call a panel rotation device. So this device on the left-hand side rotates the panels by the crane picks up the panel off the truck and places into this stationary device. They then move the crane hooks from the top of the panel to the side of the panel and then rotate on site. The reason for using this is because there was limited access for use of a franner on site, and with the stillages that Austral provided for installation of panels on site, the panels could be delivered without the use of an A-frame, but they could just be lifted off the truck and left on site, and then the panels installed at the leisure of the builder, which with a project like the WestConnex, which has a 24-hour-a-day operation, it certainly eases any contractual issues between both the precaster and the contractor, as it essentially takes away any demurrage costs for transportation and enables the guys on site to plan their day more effectively. Some other projects here, we have the M5 WestConnex. So this is an exhaust tunnel building at Armcliffe. One of the key things with this structure is that it uses double wall as a deep beam wall for 2 sides of this structure, and also has integrated buttress columns. So essentially here we have 12-meter high walls with the outer shell protruding 1.5 meters above the panel, and that allowed the installation of some large precast beams to tie into the panels. From a construction and design perspective, the key thing here is that the fixed connection with integrated buttress column allowed a modular formwork system to be used with the panels. So what we can see here on the right-hand side is essentially the 2 double wall panels with a U-bar cast in the end. A prefabricated cage was then placed on site with some of these bars in grey, untied and rotated before the cage was pushed in and before the formwork system was installed. So the advantage of this is that it significantly increased the speed of construction for the contractor. So the comparable building as an in situ structure took over 12 months to build, whereas this in double wall was approximately 3 months, which is a massive win for the subcontractor. So here's the finished result for the WestConnex building. So if anyone who ever comes out of the tunnel near at the M5 near the Sydney airport, please do have a look at it because it is quite impressive. And this building now actually has another building on top of it, housing all of the mechanical fans and whatnot for the tunnel. Here we have some basement walls for the University of Sydney done in conjunction with Laing O'Rourke. So the main advantage here is that the panels can be installed quite quickly, and the panels are suitable for use as a basement wall. So if there's any issues with waterproofing and whatnot, we have solutions and details available from Austral Precast to make that work. Another impressive project here completed in 2019 is the Military Vehicle Centre of Excellence for Wattpac. So what we have here is essentially double wall, both for the office and control station towers at each end of what essentially is a tunnel that then has a double wall and hollow core structure around the existing tunnel. The reason for this is that there is a military vehicle made on site, which is then tested. So the tank itself the cannon must be fired prior to delivery to the Australian Defence Forces. And the reason for the use of double wall here was the fact that we could reduce the spacing of the panels to the rear of the existing tunnel, and also with that achieve both the acoustic and structural requirements for it. Speed of construction. So here we have some double wall panels for the Holiday Inn Express for ADCO near Sydney Airport. So one of the major advantages here is that we can see the panels being installed essentially 50 millimeters away from the adjoining boundary of the existing building. So double wall panels here are being used as the external shear wall for the entire structure. Here we have some large spin-up panels for Estina Apartments in Penrith. So these panels arrive horizontally on the truck and then are spun up on site and lifted in place. And the main reason for using double wall here, once again, was it was on the boundary, and the contractor wanted speed and quality of construction, which they achieved very well with double wall. And a credit to Tom and the team from Estina doing a really good job there on that project. So when it comes to building with double wall, putting these panels on the boundary line is a very significant advantage in comparison to other methods. And the fact that we can core fill the panels and apply waterproofing at the joint means that the boundary or the spacing required to the boundary can be significantly reduced and really increase the time, really increase the speed and reduce the time of construction on site for the contractor. The water tightness that we can achieve is up to 20 meters of waterhead, just for interest. Here we have also some retaining walls. So we can do cantilevered retaining walls with double wall, which requires essentially a similar footing to what you would have as an in situ construction. And then just the main point would be a check by the engineer of the bending moment, particularly and shear, particularly at the joint from the bottom of panel to the footing. The other thing you can see here as well is there is a significantly reduced requirement of earthworks at the rear of the panel in comparison to in situ methods. So double wall overall is a permanent formwork system with the quality and efficiency advantage of precast, together with the engineering benefits of in situ construction. So it's high quality, Class 2 off-form finish with all the reinforcement already in the panel. And when it comes to actually constructing the panels, the structural design should be converted directly from an in-situ design, utilising a mu factor of 2 under the Australian Code. Once that design has been completed, we then put in the reinforcement in the panels as per the engineer's drawings, and with that then reduces the design process. We also have reduced trades and hot works on site, and overall the speed and efficiency of building with double wall is the major advantage of using this system over traditional precast and in situ methods. Thanks for your time, everyone.
Thank you, Matthew, for your presentations and great insights. I'd now like to welcome our second and final speaker for tonight, Angus McFarland. Angus is a structural engineering leader in Laing O'Rourke's Engineering Excellence Group. Laing O'Rourke is a multinational contracting organisation with more than 12,000 staff worldwide. Angus was chair of the Modular Construction Code Board in Australia from January 2014 to January 2017. He is a fellow of the Institutions of Structural Engineers, Civil Engineers and Engineers Australia. Angus is a passionate practitioner of modular construction using design for manufacturing and assembly. He specialises in promoting the use of DFMA methodology in major construction projects, including buildings and large-scale civil engineering works. Angus was a member of the steering group and is a contributing author to the Concrete Society's Guide to Design of Concrete Structures in the Arabian Peninsula, which was published in October 2008. His paper on the design of high-strength concrete columns was published by the Institution of Structural Engineers in March 2007. Please welcome Angus McFarland.
Good evening, ladies and gentlemen. My name is Angus McFarland. I'm structural engineering leader with Laing O'Rourke, and today I'm going to give a presentation on double wall. The subjects for the double wall presentation are shown here. I won't bother reading them all out to you, but the important ones are DFMA technical specifications, what is double wall, and the case studies. Now, an introduction here gives you a summary of my experience. I've worked for approximately 20 years in the Middle East, mainly in Dubai, but a little bit time early on in Saudi. And then I worked for 1 year in South Korea. Then I've been for the last 8 years with Engineering Excellence Group in Laing O'Rourke in Sydney. And this is one of the projects I dealt with. If you look at the cursor here, my office is roughly where the cursor is, halfway up the right-hand side of the building. Now, these are some of the projects I worked on in the Middle East with Atkins, the Burj Al Arab, with Haider, the Emirates Towers, and again with Haider, the Burj Khalifa, which I still think is currently the tallest building in the world, though it'll probably be surpassed by the Jeddah Tall Tower now. However, out of these projects, my favourite one was the middle one, the Emirates Twin Towers. It was built within budget and finished 3 months early, and there were hardly any claims at all on the project. It was an absolute fabulous project. Now, in my introduction to double wall, it was actually Laing O'Rourke's version of it, which we have in the UK, which is called twin wall. And in this twin wall, it was going to be used on Beckton treatment works, the sewage treatment works in London in the UK. So I was called in to do the peer review of the design calcs and carry out the water testing of the prototype tank. And you can see the photograph of the prototype tank there. Now, I mentioned at the start the DFMA technical specifications. This is a project that we're doing with Standards Australia. And what they want to do is try and unlock or facilitate the use of off-site construction. So we're currently looking at 3 standards or specifications, and there could be more depending on the progress of the project. Pardon me. The 3 we're looking at is progressive collapse, precast wall elements, and loading. And I'll discuss these in the following slides. Progressive collapse, if you look here, we've got 2 models of buildings. This is a steel frame modular building, but it could equally apply to a reinforced concrete building. The left-hand one has 200 by 200 by 6 columns in the middle, and the right-hand one has 300 by 200. And you'll see when the row of columns along the bottom right-hand side is removed, the one with the larger columns remains standing. This was a PhD project we did at Monash University in 2016 when I was chairman of the Modular Construction Code Board. Now, the technical specifications, one that I'm doing at present is a mock-up of a Eurocode, EN 14992, pardon me, this is not unusual for Australian standards to use Eurocodes. There's a crane standard, 1418.11, I think it is, which uses a facsimile of a Eurocode. So I'm doing this to let the members see that we could get to a standard quite quickly. So the aim is to either do a technical specification or a standard adopted from the Eurocode. And thirdly, what I'm looking at is loading. AS 3850.2 gives some guidance on loading, but it doesn't really give enough, especially shipping loading and rail transport. Also, with modular construction, I know that Hickory Construction and Hickory Building Systems in Melbourne did a hotel in Port Hedland in WA, and that travelled nearly 6,000 kilometres by road. I think it's 5,400 kilometres by road, and I think the fatigue loading would be horrendous on those modules, especially since most of the roads in the outback are dirt track roads. Now on to what is double wall. Well, quite simply, a double wall is a precast component. It comprises 2 reinforced concrete shells, which you can see there, and they're joined by a lattice girder. Then on site, the space or the core between the shells is filled with in situ concrete. Now here's how a double wall works. First of all, you cast the slab with the lattice in it, and that's similar to the lattice girder you can see in the photograph on the left-hand side. You then cast a bottom shell and mate it with the top shell, which is already matured concrete. Then vibrate the whole lot so that everything, all the concrete is compacted around the trusses. Now here are the components of the double wall. You can see the internal reinforcement, the lattice girders and the precast shells, and there's a typical installation on site. Now I show a short video here of our precast facility in the UK. This doesn't just do, I've turned the music off deliberately because I don't think it's come over very well over the internet. But you see the high-speed carousel, which brings the concrete to the batching dispenser or the concrete batching plant itself. These are all robotically controlled. Now there we're pouring the initial shell of the double wall. This could be any precast component. It could be a slab component as well. The reason I know it's double wall, because you tend to have a double row of lattice girders at the edge of the double wall. As I say, there's not a lot of labour involved in this. It's most of the labour run the robotic control systems. There is some labour, but we try to do as much of it by robots as possible. Then to speed up the strength gain of the concrete, we've got curing chambers, which are obviously heated up in the UK. Now you can see the double wall components. Well, it was twin wall in our case, but it's the same product. Twin wall is just the laying rope name for double wall. Then this is the mating process of the two shelves being brought together. Now you can see the mature shell on the left hand side. Unfortunately, the video I've got didn't show it getting flipped over onto the other shell, which is a bit of a pity, because that's very interesting. But you can see there's a completed product there. Now, design and testing, as I mentioned earlier with the Beckton treatment works, the trial wall, there's a lot of testing done at University of College London, it's a UCL. Mainly the testing was a shear interface test to check that we could actually get composite action, and other parts, the key aspects of those tests are the roughness of the concrete, the strength of the core and the strength of the shell concrete, the embedment depth of the lattice trusses, and the diameter of the lattice trusses. So those were all the variables that were used. There were hundreds of tests carried out, and I just show a summary of a couple of tests. The left-hand side here is concrete at various strengths. The 50-50-50 is 50 MPa concrete in the shell, the core, the shell. The 50-10-50 is 50 in the core, 50 in the shell, 10 in the core, and 50 in the shell again. And then we've got the various roughnesses. That's the roughness on the inside of the concrete shell. Now, the reason for this testing and why it's applicable to Australia is the Australian Concrete Code, AS 3600, uses the Eurocode 2 equations. It's the 2018 version. So you can see that there in table 8.43. Now, AS 3600 doesn't explain the roughness very well, so I've put in what the roughness from the Eurocode is 3 millimeters. I think the roughness would probably come out in a commentary to the code, which I haven't seen yet. But for double wall, we use these parameters, which are very good. Those are the second highest parameters you can get. If you look down the bottom here where my cursor is, the highest parameters are for monolithic construction, which is 0.9 and 0.5, versus 0.7 and 0.4 for double wall. So we get very nearly completely composite construction. Now, I'll go on to some construction details just to show how flexible it is and how similar it is to to in situ construction. Here we have a plan view of a vertical joint, and you've got the double wall diagonal trusses there, and all you do is drop in a reinforcement cage down that gap to make it a monolithic wall. And if you're looking at section AA, which is that's a horizontal joint there, your cage goes into just a lap length. If you need to have additional reinforcement, you can actually put it the full height of the wall if you want to. Normally you would do most of that in the factory and only drop in these cages at the joints. Corner joints, again, virtually identical to corner joints in situ construction. Here you have 2 layers of reel, which is a standard reinforcing detail. And in this one, we've only got 1 layer of, well, 1 L bar in the joint. And occasionally, if you're doing very high pour rates, that's with very high walls, then you may want to put in some reinforcement, not reinforcement, some corner plates and structural steel to stop the joint from failing. Again, a T-joint, again, it's similar to in situ construction. You just drop in your reinforcement cage in the joint there. This would probably be typically a full height cage, because it's probably there to resist opening or various other structural forces. Wall to slab joints, it's best to stick to floor height if you can. It makes construction easier and you can get your connections easier. So you avoid double height walls unless there's no slab connection at mid height. The continuity reinforcement will be placed after you've got your working deck down for your slab. And it's always good to extend the outer edge of the wall so that it works as a permanent formwork for the slab. It makes the on-site work easier and allows the full height of full effective width of the wall. However, one of the things I prefer, which I'll show you in a minute, you've got lattice plank or preformed slab systems such as hollow core or bond deck. You oversail the top of it. That means you can get greater installation tolerances and make the concrete the same strength as the core concrete, the same strength as the slab concrete. Consider that in the design calcs. But as you saw in the testing earlier, the core concrete doesn't influence the overall strength of the wall by much. A personal choice for me is you put neoprene strips in there. That prevents grout leakage, but the trade-off for that is you've got reduced wall section there. But that's not usually a problem because that's usually just pure crushing, whereas the wall will be designed for buckling elsewhere, so you'll probably find that reduced section there is the same strength as the full section elsewhere. Now, transportation and delivery, just some key points here. I'm saying the panel height is 3.5 meter max. That's usually for transportation. That might very well be the width of the panel. You might want to go longer, you know, if you're doing double height. But so that'll get worked out for you by the double wall people. So the maximum trailer can carry is about 3 panels, 3.4 meters by 6 meters. You can do other things if you get special permission for transportation. But as a rough guide, that's about 20 tons weight. Now, these safe access trailers are really appreciated by the crane teams and the dogmen. It allows them to get easy access and very safe access. There we go, just lifting the thing in. Now, temporary works, I'm not going into too much great detail or great detail to the temporary works, but it's best to sequence the wall after the slab's done. If fixing to temporary blocks or in trenches or whatever is not usually as good. Sometimes you need to do that depending on the construction program. But if possible, you should try and sequence the work so you do it from the permanent slab. And finally, just for health and safety, corrosion protection of the bases, you'll need to put barriers in here if plants moving around or something else to restrict plant from collisions with the double wall until the concrete core has cured. Now, corners may require temporary steel brackets, as I mentioned to you earlier. Or wall ends, you can fix ply onto the end if you want. Or quite often what we do if it's inaccessible, instead of the ply, you can put mesh in there. That is cast in the factory, and that acts as a stop end shutter. Or an alternative, and this is an alternative from the double wall website, is you can use this permanent edge formwork, so it's proprietary permanent edge formwork, which is specifically made for the double wall and eliminates the need for on-site formwork or mesh. Now we'll go on to some case studies. The first one's from the UK. It's before I joined Laying Rock, I was still with Hyder, but this is one of my colleagues, and he worked on the Durham University Library. It was a fully precast solution, because at Laying Rock we believe in DFMA and off-site construction as much as possible. We try to get about 70% of our work off-site if we can. Now this is a solution here, fully precast, and there are 119 twin wall panels. Now you can see that the panels there in blue, then the different panels, 1 story in grey, 1 story in blue. Those are the twin wall panels. Now what's interesting about this job is you're not restricted to rectangular shapes. It's normally best if you can go rectangular, but you're not required to go rectangular. You can see this shape here, and even this back wall isn't rectangular. It's got a small dog leg in it. Now, here I'm saying the stair adjacent to the existing building is an excellent application of twin wall. It avoids a lot of temporary formwork. Now this is doing what I'm saying you shouldn't do, is do double height, but it's because there are no half height panels. So to get over the double height, we had to put in an extra row of props, and to pour the concrete, use the scissor lift to get in access into it. And the stop ends were done with mesh, so you didn't have to go back and fix formwork at height. Now this is the Beckton treatment works, the sewage treatment works that I mentioned at the beginning. This is when I first got involved with twin wall. It's the largest sewage treatment plant in Europe, treats 305 million people per day, just a little bit less than Sydney. And at that time it cost $350 million. The twin wall was used in the aeration tanks, which are shown here. Now there are the aeration tanks, and that's the trial tank off the aeration tank. One of the things I didn't mention, we did these long walls here, we did 2 types of wall, one horizontal twin wall and one with vertical twin wall. This column here is just measuring, it's got a deflection gauge on it to measure the deflection of the wall when this tank is filled with water. And it's basically to prove the tanks were waterproof. It's done to the IE Institution of Civil Engineers specification. It's filled with water, no internal waterproofing. And I think if less than 10 millimeters of water leaks out in 2 weeks, then it's deemed to be waterproof. So it might be 2 weeks, it might be 3 weeks, but I'd need to check up the specs. But the test was a resounding success. So the original design was by Arup. The original design would have been by Hyder, and Laying Rock wanted my team, Hyder Dubai, to do it, but I wasn't allowed to do design in the UK by Hyder UK, and so the Hyder UK people didn't get to grips with it as well as we had. So Arup got the job and made a very good job of it. Now here's the alternative, the twin wall or double wall design. One thing I didn't mention, one of the drawbacks I'll say currently with double wall and twin wall is the maximum thickness you can get is 400. Quite often on taller buildings, I would like it to be 600. So to get the moment of resistance, we needed to use buttress walls. And I'll show you some buttress walls later on, not in this project. But the overall solution, we saved 50% reinforcement, not a huge saving in concrete, only 10%. And there was a large saving in the program, which was the biggest saving, but I don't have the figures for that, unfortunately. But it was significant program saving as well. So overall, it was a resounding success. More up to date, you'll be glad to hear, in Australia, this is the University of Sydney, where we used it in the basement here of the ETP. We also wanted to use it in the core walls for the building. The ETP's the Engineering Technology Precinct building, which is currently nearing completion. But our engineer was reticent to use it as structural core walls or shear walls, which is one of the reasons why we're talking to Standards Australia to get this design in so you can use it as a fully composite wall. We want to get all stakeholders in, not just some engineers believe it's fantastic and yes, you can use it fully compositely. Other designers are a bit reticent, and our designer on this project is a bit reticent. So the technical specification or the new technical standards will hopefully get over that, and we want to get some of the more reticent engineers to be part of that approval process so they become stakeholders in it, and we can actually answer their queries during the project's progress. Now the key features of the double walls you'll see here, there's the starters. These are the single row starters here. It provides the flexibility of in situ concrete, no shuttering required, and it's quick to erect. So you just drop them onto there, prop them, then fill them with concrete. Now here's another one which I'll show you. This project's still underway. We're still doing the value engineering on it, but it's an iron ore project. I won't mention the name of it because that's confidential, but it's fairly easy to work out where iron ore projects are in WA. And this is the main crusher, which the crusher iron, the rock before it gets sent further down for processing. And this is a concrete vault in reinforced concrete, 1 meter thick concrete walls, and I think they're 800 thick here. So we had a look at double wall. We also looked at a shell wall, which is like double wall, but you put one shell up, fix in your reinforcement, put another shell up, then pour the whole lot together on site. It's a bit more time consuming than double wall. And we looked at solid PC. And our value engineering exercise showed that double wall was the best. The pardon me. The costs were initially about 50% higher, but we revamped the buttresses and got it down to about 20% higher. And when we go through another round of value engineering, we should get them very similar to the Insitu. The big thing for us is there's a 10-week saving in using the double wall. Now, don't forget, that'll be sticking the double wall in a ship from here in Sydney, because Austral's factory in Perth doesn't do double wall, and then offloading it and then taking it to this iron ore mine. So that's great. Currently, the program savings outweigh the cost of the double wall, which is good. So we just need to have a look at a few other things. one of the things we're looking at is there's a lot of vibration in this being a crusher. So we need to make sure the natural frequency and the dynamic performance of the double wall, which is significantly lighter than in situ, is satisfactory. But we're just dotting the I's and crossing T's on that, but that's looking promising. Now, I've almost finished now. It didn't take too long at all. I'll just do a quick summary of some of the things I've mentioned. The installation program, this is what we find, and no doubt Matthew in his other presentation can give you information for Australia. In the UK, we allow for 30 minutes per panel, but you can usually half that. You can usually do a panel every 15 minutes. I recommend using self-compacting concrete or something very similar to it, and normally 10 millimeters aggregate. That makes sure your concrete core is completely compacted with no voids in it. Keep the wall panels simple as much as possible. You can cast in items, especially with digital engineering and your BIM or your digital engineering models or BIM, but it needs more coordination, and you're far better. Keep it simple on site, and it means less design coordination and it's more reliable results, less mistakes basically. And visible joints, if you're exposing the joints, try and keep them simple in one plane or the other plane. Don't try and expose them in both. Now that's the presentation pretty well finished. To sum it up, is the benefits of double wall is it has the flexibility of in situ concrete, but it comes with the speed and simplicity of precast. Thank you very much.
Thank you. Thank you for those great presentations. Yeah, extremely informative, and we've had heaps of questions, so that's really great. Our speakers will now come together to take questions from you, our audience. We did ask for people to put forward questions on registration, so we have some of those. But we've also had a lot come through, and we haven't got a lot of time, so we'll get through to as much that we can. So if you could send your questions via the chat box, and we'll pick them up this end. Thank you. We've talked in this presentation a lot about AS 3600, and I wanted to sort of start with the standards and start with Angus. We talk about, putting double wall in context of the standards, and we had a great question from Michael in New South Wales, was asking, can the double wall precast system be reinforced and detailed to comply with the earthquake requirements of AS 3600 2018 for structures over 4 stories? Angus, would you like to answer that one?
Yes, it can. Can you hear me okay?
Yes,
Yep.
we can hear you.
Yes, it can. I think the details in Matthew's presentation were slightly better than mine, but you can. Double wall is actually easier to design to the earthquake standards in AS 3600 than solid walls, because you have a problem with the solid walls at the joint in the base or in the joint between them. So yes, it can.
Thank you. Matthew, do you want to comment on that at all?
Yes, thanks, Amanda. So thanks, Angus, for your presentation. That was really good. When it comes to the particularly the boundary elements, we can incorporate ties and have the U-bars that make the panel-to-panel joint essentially to encapsulate the vertical bars of the reinforcement. So that way we can meet the requirements there for the boundary element sections, and that confinement is obviously very good for the earthquake position to stop any buckling of those main bars out of the concrete.
Thanks, Matthew. And staying on AS 3600, Catherine, who's in Queensland, Catherine's asking, can the system be designed in accordance with AS 3600 concrete structures, or would its design and use in Australia rely on Eurocodes?
Can I answer that first then, Amanda? Or is it Matthew? Sorry.
Go for it.
Yeah, I touched on it in my presentation with the AS 3600 2018. The table that I showed in the presentation is actually based on Eurocode. So the Eurocode parameters are used in Australia. So, and that's why I mentioned the testing that I'd done with UCL in the UK to Eurocode. That testing actually satisfies a lot of the testing requirements in Australia. So what I mentioned on the University of Sydney, our designer there was reticent to use double wall in the core walls, but there are other projects, and I'll let Matthew talk if he's got some details of them. Lots of other engineers here use them in core walls. They don't have a problem. So it's an emphatic yes, it complies with AS 3600.
Thank you for that. Just going back to the presentation, Matthew's presentation, thank you, that was great. Nicole is asking that, Matthew, in your presentation, you said it was waterproof. Does that mean it is suitable for basements, or can waterproofing be applied in the factory?
Thanks for the question, Nicole. So when it comes to waterproofing, as you might have seen there from Angus's presentation, the biggest thing that will dictate that will be the overall thickness of the core concrete, and with that, traditional waterproofing can be applied as you would have, say, for an in-situ wall. So you can have the application of water stops and whatnot between the starter bars at the joint. But the best thing for waterproofing typically is more concrete in the core. So from our perspective, when we're doing waterproof structures that require waterproofing, we typically start with a minimum overall thickness of the double wall at 250 millimeters plus, and that enables us to get more concrete in the core. Most builders in Australia will then want to have a belts and braces approach. So the increase of the thickness of the panel, making sure we have good concreting of the core, and then they will typically apply the water stop and a bituminous impregnated foam cord at the joint as well.
Matthew, perhaps can add to that is the sewage treatment works in Beckton. That didn't have any waterproofing, and I didn't mention in the trial prototype test we were doing, we put some water stops on one side and no water stops on the other side, and the treatment works was built without water stops, so it's relatively waterproof for an industrial sewage treatment plant application. It's probably not waterproof enough for if you wanted to keep dampness out of a basement.
Thanks, Angus. Thank you for that. And just don't go anywhere, Angus, because we've had a question from Asborn who's asking, do you guys have noise transmission data for a double wall, and has any noise test been done?
Any what? Sorry, I didn't quite hear that.
So the question is do you have noise transmission data for a double wall, and has any noise test been done? And that was directed to you, Angus.
I don't have the noise transmission data, so I can't really answer that question.
I might be able to help you there, Angus. So we've engaged some reports for the acoustics of the double wall, and essentially it becomes the same as any concrete structure. So for instance, a 200 mil thick wall have an RW plus CTR of, I think it's 54, and going right up to an RW plus CTR of 63 for a 400 mil thick wall.
Thank you for that, Matthew. Stay there, Matthew. Eldorado has asked a question for you, referencing your presentation. What is the benefit? What's the benefit of this cavity compared to standard precast walls?
Sorry, can you repeat that, Amanda? I just missed that last bit.
So the question is, what's the benefit of this cavity compared to standard precast walls?
Thanks. So the main benefit of core filling the wall on site is that we essentially have a connection of concrete and reinforcement for the panels, and with the girders and the steel across the joint, we end up with a composite structure. So the main advantage of this composite structure versus your traditional precast is that, as Angus was saying before, under AS 3600, the design is actually easier to do with double wall because it's more like in situ, and we can use it to detailing with a limited ductility factor of 2, whereas traditional precast, I think, has a limited ductility factor of 1, making the structure, requiring the structure to be much stiffer compared to double wall under earthquake conditions. Then the other main advantage is the mass of the wall is independent of the overall thickness of the wall. So traditional precast, the thicker the panel is, the heavier the panel. So that is why predominantly in Australia, most precast is typically limited to 150 millimeters to 200 millimeter thick walls. Whereas with double wall, our 400 millimeter thick wall has the same mass as a 150 mil thick precast wall. So when it comes to the efficiency of construction on site, the overall size of the panel can be much larger, which actually makes it cost effective to actually manufacture and construct buildings and other structures with double wall compared to precast.
Thanks for that, Matthew. And I think this is one for you also, and it's coming from Syed. And both of you talked about pour rates. And Syed's asking, what pour rate do you as a manufacturer recommend?
So when it comes to pour rates, we use the tables available under EN 14992, which essentially gives us the pour rates based upon the spacing and embedment of the girders. And typically, where most projects we're going between the 1.2 meters to 1.5 meters vertical lift per hour, with the overall lift height being determined essentially by the type of concrete that we're putting in the core and how quickly that goes off. So a good way to test that before you start your project is to request a slump retention graph or similar from the concrete supplier if they have it available, because then you can actually see how the concrete will perform over time, and that can help you determine exactly the maximum limit of the height that you can pour the wall to.
Thanks, Matthew. I'll leave it up to you guys to who answers this one, but it's coming from Edward. Thank you, Edward. And Edward is asking, how is the mesh bound to the starter bars? I think it was your presentation, Matthew, but I'm sure Angus could have some input there too. Matthew.
Do you want this one, Angus, or do you want me to take it? I'll take it.
I'll let you answer, Matthew.
Sure. So the mesh itself is that we're putting in the joint is lapping. So, for instance, the starter bars in the base of the panel are not tied to the vertical bars in the panel. There's essentially a full tension lap is the lap length that you would apply to that instance, and the lap is going from, for instance, the bar in the core to the bar in the precast. At the joint, to control the location of the double wall, we can use a wagon wheel spacer or similar to essentially make that mesh central in the joint if need be. But the cover of the mesh in the joint is not an issue, and the mesh itself is a welded assembly on our mesh machine. So for that, we would have, for instance, an N10-200 bar mat that's made on our mesh machine, and that's placed in the core. So the mat itself is all fully welded before it goes to site.
Angus, do you want to add to that?
No, that was a very good explanation. I don't need to add anything to it.
Okay, thank you. We've had a great question, and Angus, you talked about transportation towards the end of your presentation. We've had a question that's come in to the effect of transport and delivery of the precast concrete. Do you require a transport permit and transport insurance prior any transport commences as part of risk assessment? Great question.
I'm not an expert on transportation. I tend to look at the loading. We have other people in League who look at the transportation. But off the top of my head, the 3.5 by 12 meters is the largest you can get on a truck without any special permission. If you're going longer than that, you need a police escort. I forget which length it is, 14 or 15 meters. And after that, the other thing I've found, it varies from state to state. It's not Australia-wide. So if you're transporting something from New South Wales to WA, there could be 3 or 4 different regulations you've got to meet. So that's all I can say. It's a specialist field.
Yeah, thank you. Thanks for that. Maybe you've covered that off, but I think we have got a great question that's asking what is the maximum height of the panel that can be safely transported? And is there a limit to fabrication of the panels? Angus, can you keep going on that transport topic?
I'm not aware of any limits to the fabrication of the panel. It's 3.5 wide, and as I say, normally 12 meters long. Matthew, what's the longest panels you've done?
We've manufactured up to 13.2 meters in overall height, because our beds are 13.5 meters long. You typically, with your lifting system, will be limited to about 32 square meters, which is roughly 11.5, 12 ton with the double wall. So the overall width will then obviously decrease for those really, really high panels. The major thing to consider is for double wall, you want to minimize the amount of joints. So going double wide, a double wide panel would essentially be a better construction method than having triple height spin up panels, because you'll end up with less joints, making the construction easier on site.
Good.
Thank you for that. We've had this question come in a lot, and so I'm going to ask it to whoever wants to pick it up. And the question that's being asked is, can we get the same strength in a double wall as from a concrete wall?
I can answer that from all the testing we've done. Yes, you can. It's a fully composite wall. So once the concrete in the core has matured, it's the same strength as a solid wall. But one of the things we found, and I don't know if you picked it up on the testing there, quite often we don't do it, because you normally have I would suggest you do the concrete in the core at least the same strength as the concrete in your slabs. But basically what I'm trying to say is the core concrete doesn't necessarily need to be as strong as the concrete in the shells. But yes, you can. It's every bit as strong as a solid wall.
Thanks, Angus. And as I say, thank you. We've had heaps of questions, so I'll move on quickly. And this one's directed to Matthew, and it's around thermal insulation. And Rafe's asking you, Matthew, how efficient is double wall with thermal insulation and heat exchange?
So the double wall, in its standard form with just the precast shells and the in-situ core, is the same as a concrete wall. So you'll have the same transmission of any temperature from inside to outside, just basically based upon the thermal mass of the concrete. With double wall, though, we can also put insulation in the panels, where essentially the external shell would be your 60 or 70 mil thick facade, with then essentially insulation in between, which is held to the internal structure by composite pins. So the internal shell of 70mm plus whatever the core thickness is becomes your structural wall. So in that instance, we can actually have a structural wall as well that is insulated, and I believe that this is a product that we'll be bringing to market next year, which will essentially have the benefits of an in situ wall, but also with the insulated properties and a vapor barrier caused by having that insulation in the panel itself.
Great, thanks for that. Another question that we've had a few times is, and I'll read actually from David's question. Thanks, David. Asking, what are the advantages compared to plastic competitors? Angus, do you want to talk about that a little bit? They're citing Denselot.
Well, not really. I've looked at the plastic competitors. It's basically, I mean, all I'll say is horses for courses. I'm a concrete and a steel man, so I prefer to use stuff like that as opposed to the plastic. So that's all I can say. But I wouldn't rule out plastics.
Thanks, Angus. We've probably got time for just a couple more questions, and we have had a question about how do you guys identify what should be the grade of the concrete while constructing the double wall? Does it depend on the height of the building, or is it the same for all double walls? Matthew.
So for us, the structural capacity of the wall will be determined from the structural engineer's calculations, and so typically there'll be double wall specified. It could be 65, 50, or 40 MPa. And to Angus's point before, the concrete in the core has less of an effect on the overall structure compared to what's in the panel. So our basic standard is to construct double wall using 50 MPa concrete for the shells. But if you need the driver of that is the early lifting strengths for manufacture. But if you need a 40 MPa wall, then all you do is put a 40 MPa in the core, and that minimum, whichever is the minimum value, is the conservative way to design the wall.
Thanks for that, Matthew. We talked a bit about thermal insulation, and Engineers Australia is running its Smart Climate Change conference later this year, and an expansion on that question that's coming from Nick is, are there any further sustainability benefits from using this system? Less concrete, opportunities for lower carbon concrete, less steel? Matthew.
Thanks, Amanda. So when it comes to the actual overall construction process, because we've got our own mesh machine, which makes the reinforcement off of coil, we have a significant reduction in waste when it comes to manufacturing the steel that's in the panel. For concreting, the concreting that's done in the factory has another significant reduction of waste because it's essentially batched and put into the panel. I think it's 6 minutes after the batch is started, and so because of that, we can actually have a lot less wastage than we would have, say, compared to building everything in situ on site. When it comes to the sort of carbon benefits and those sort of things, I think we're yet to see any really good concretes that have early age strength abilities, high early age strength abilities with low carbon content, as typically a lot of these recyclable concretes that I've seen have a much higher fly ash content or similar that reduces the early age strength of the concrete. But be happy to have anyone show us point us in the way of anything new in that, because the precast industry really needs something in that area.
Perhaps I could come in there as well. I agree with off-site manufacture, be it double wall, twin wall, or whatever. There is less wastage when compared with in situ construction. But also when you're looking at the savings, I just go back to the Beckton treatment plant. We use 50% less reinforcement and 10% less concrete.
Thank you. Thank you. That's a great statement. That's great to hear. You know, it really is. I just wanted to finish sort of a little bit where we started with this event, when we were planning this event. Obviously, there had been a change in the standards, Angus, that you've been working on. Do you want to just quickly just talk to us about what you think will be the biggest benefit from those recent changes to the standards with regard to double wall?
Well, it's not just double wall. What Standards Australia have come up with is that there are one or two precast wall standards, but they don't go far enough. And Standards Australia are trying to encourage off-site manufacture, you know, DFMA, and that's why we're working with them. And the reason why we picked one of them, the double wall one, was because some engineers or some designers are reticent to use it properly, i.e. in core walls and shear walls. So if we can get that out, that would help that. Then we'll see how the project goes. But it won't just be a double wall project. I think it'll be quite a large project for Standards Australia. Probably we're targeting 18 months for the first part of it. It'll probably be a 5-year project, maybe longer.
Thanks for that input, and thank you to everybody for sending through questions. And unfortunately, we have run out of time. Please, I know you'll join me in thanking Matthew Murray and Angus McFarland for their time and two really great presentations. Thank you so much. As the construction, thank you. As the construction sector continues to boom, we are responding to that. Obviously, as the profession, the sector has to meet increasing demand, the opportunities, but there's also a lot of challenges with that. So we're hosting a groundbreaking, excuse the pun, webinar next Wednesday to raise awareness and debate with you, our audience, on the opportunities and challenges. We have amazing speakers from Infrastructure Australia, Multiplex, Arup, Inhabit Group, and architect from Woodscabot. Please don't miss out, and if you could register in the description box below. Once again, I'd like to thank our long-standing industry partner, Austral Precast, for making tonight's webinar possible. So from all of us and from Engineers Australia, thank you very much for watching, and we look forward to seeing you all again next week. Thank you.